Thanks, Ron. Yeah, so it's a real pleasure to be here to be part of this celebration for Avi. Let's see, when I arrived at Rutgers as an assistant professor in the math department a long, long time ago, my first course I was assigned to teach a calculus class, and I met my TA, who was a master's student in the math department, and it was a visibly pregnant woman who at some point, she said, you should really meet my husband. He's a graduate student in the Princeton Computer Science Department. You'll like him. And, well, she was right. And and that meeting also kind of, impacted the direction of my research, where I kind of started in pure discrete math and kind of slowly got corrupted into being a computer scientist. Over the years, I think, many people have benefited. One of the things you benefit from Avi is just the problems that he spews out. And so I've found those always very enticing. And what I'm going to talk about today is another example of a kind of enticing problem that I heard from Avi. And it led to a couple of papers, one with Ankur Moitra, who was a postdoc here a few years ago, and the other with an Injidi, who was also a postdoc here at the Institute and then at DIMAX, and my student, Sijin Tang. Okay, so let me just start with a warm-up. This is kind of a classic, very basic statistical learning problem. You have an unknown probability distribution on some finite set S, and think of it as just a function mapping the set to probabilities. And you observe samples from F, and then you want to put an approximation to the probabilities for all the points. Okay, so, we want an estimate F equals of S for each S, and we have some estimation parameter, which is how close we want things to be, so we want our estimates of all the probabilities to be within epsilon for all S, and that we should be correct with some high probability. And then the format of the output, I want you to think of that you're going to output a subset of the universe, S, and then for each element S of this subset you output, you should output your estimate. And for everything else, you output zero. It's implicitly zero. You don't actually have to say zero. So you should think of, let's say, the support of the distribution is much smaller than the size of the set. And we'll see this in the example that we go. So, all right, so this is like a classic, very old problem. And of course, the algorithm for doing that is, well, just watch the process for a while and compute the empirical frequencies for all the, for your observations. And you'll get pretty good estimates. And, the running time will depend on how good an estimation you require, but it's polynomial in 1 over epsilon. Okay. So now we have this meta question, which is, well, can we efficiently estimate F? Now suppose we're in an environment in which each individual observation is corrupted or distorted. And so it's the earliest that I know of, which that it's mentioned, and this is I have this reference was from another paper, which I'll mention later, but in the learning theory community, they have a formulation of this. Okay, next slide. Okay, so a few years ago, Avi with Zevdir Anuprao and Amiria Hudayev, maybe they're all here, defined the following kind of idealized model to study this issue. Okay, so you have a probability distribution defined now. Now your universe is the set of binary strings. Okay, so it's an exponential size universe. We think of n as our parameter. And the sample, yes? So that's a sample from the distribution, but you don't get to see that. So, well, there are two versions of the model. In the first model, some of the positions are just erased. So what you see is some question marks in some of the positions. That's the lossy model. And then the other model, which is noisy, is, well, that's even harder. You don't see question marks. What happens is for those positions that got corrupted, they're just replaced by a random coin flip. Okay. And so, okay, we have a reliability parameter mu, which sort of, in the lossy model, each bit is erased with probability 1 minus mu. So think of mu large is less noise. Mu equals 1 is no corruption. Mu equals 0 is complete corruption. In the noisy model, instead of the bits being erased with that probability, you replace them with a random coin. And the goal is to, again, recover the distribution now in time, let's say polynomial in n, which is the number of bits, and 1 over epsilon. And we'd like to do this for any fixed mu greater than 0. Okay, so, all right, so that's our goal. And so this problem was studied in both the lossy model and in the noisy model. And in the lossy model, it's, well, you could say it's completely solved, but problems are never completely solved. So it's mostly solved. And the techniques are sort of, perhaps, well, linear programming is not so surprising. Complex analysis is a little surprising in the context of this problem. All right, and then the other thing, in the noisy model, well, that's partially solved, mostly solved. And there, the techniques are some Fourier analysis, Mobius inversion. And then one ends up having to reuse the results from the lossy model as well. So we need linear programming and complex analysis. Okay, so the plan for the talk is I just want to give an overview of the solutions for both cases. So I'll say, this is not, a birthday meeting is not the greatest place and not a good place to give a very technical talk. So but the solutions are technical. So what I want to do is not, I want to tell you what happens in the solutions, but I'm not going to show you the technical details of what happens in the solutions. Okay, so let's go on to the lossy case. Okay, so again, the lossy model is that some bit positions before you observe get changed, replaced by question marks. So we want to recover in time polynomial in n and 1 over epsilon. And the first result in this direction was this DRWY paper, where they did it provided that mu was large enough. So again, mu is your reliability parameter. And if it's at least 0.365, and then the next result, so that was improved to a lower mu of 0.293. And then the next result was my result with Anker, which did it for any mu greater than 0. Okay? Next. Okay. So I want to, sketch some of the ideas of the proof. So next. Okay. So first thing is we're trying to reconstruct the value of the distribution at every point. Well, pick one point and try to show how to reconstruct that value. And without loss of generality, it'll be the 0 point, because you can just, okay. So I want to reconstruct the value of the 0 point, I mean the point which is all zeros. Okay. Well, what do you have available? Well, you have these samples, and what I'm going to look at is I get a sample, and it's got some zeros and ones and question marks, and I just count how many fractions. The only thing I pay attention to is how many ones in the sample. I ignore zeros and question marks I treat the same. Just look at the ones. And AJ is going to be the fraction of observed samples with exactly J ones. Okay. So now a question is, how can you best estimate f of 0 from these numbers aj? And then, well, how many samples are needed so that the estimate that you get is probably accurate? Okay, so there are the questions again. And if you look at this, well, you can write down, and anybody here could write down, a linear program, which, given the AJs, figures out the best estimate of f of 0. Okay? That linear program will depend on the parameters mu and epsilon, mu being the noise parameter and epsilon being the reliability parameter. And when you write down the linear program, the value of the objective function is, well, that wiggly equals is very wiggly. But the minimum value of the objective function roughly corresponds to the number of samples that you need to do your estimate. Okay? All right, so we have this linear program. The minimum value of the objective function is the number of samples. And now, in the original paper by DRWY, what they did is essentially was to construct an explicit feasible solution for that linear program. Okay, so they kind of found the right, some set of coefficients which works, and the objective function value was polynomial in n and 1 over epsilon. That's good. That means that was the complexity. The only catch was that it required the analysis broke down if the noise parameter was too big. It was bigger than 0.365. And then there was a follow-up paper which analyzed the same feasible solution but improved the analysis and lowered it to mu greater than 0.292. Okay. So what do we do? Well, so if you have a linear program, the second thing you do besides looking for feasible solutions is to form the dual. So you look at the dual of the linear program, and, well, I'm trying to upper bound. This is a minimization problem. The dual is a maximization problem, so I want to upper bound the maximum value. Now, I want to point out that what we're doing is kind of the reverse of what people usually do with linear programs. Because usually, if you have a minimization problem and you want to prove a lower bound on the solution, right, then when you form the dual, you get a maximization problem, and then any feasible solution of the dual provides you with a lower bound. Okay, we have a minimization problem, and we want an upper bound on the optimal solution. And already in the primal problem, constructing feasible solutions is what you want to do. So dualize, now you change a find feasible solutions to a problem of I have to prove for all feasible solutions of the dual that something is true. That seems to be going in the wrong direction, or at least the opposite direction of what one usually encounters when you use LP duality. Okay, nevertheless, we forge ahead. Okay, so we form the dual LP, and what do you look at you take the LP and you get some variables and some constraints, and you stare at it for a while, and you say, okay, what can I do with this LP? So then you massage it. You replace some of the variables with other variables, and and then you transform it, and now we have a new dual reformulation. And the new dual reformulation, the objects you're optimizing over are univariate polynomials. Okay, and so the LP looks like this. You want to maximize the value of this difference, which is P of 0, which is the value at 0. That's just a constant term, minus epsilon. Now, that particular norm refers to the sum of the absolute values of the coefficients of the polynomial. Okay, so you take the constant term minus epsilon times the sum of the absolute coefficients. And now the constraint on the polynomial is kind of a awkward one to work with. You look at the transformed polynomial, which is P with, you plug in 1 plus mu times x minus 1. That gives you a polynomial q, and now I require that the sum of the absolute coefficients of that polynomial is less than or equal to 1. Okay? Now, as I say, this just emerges if you form the dual and stare at it for a while, and then it reformulates as this. Okay. So now we have the following setup. The complexity of the best algorithm is essentially bounded above by this particular maximization problem. And the question is, okay, how do we upper bound? How do we get an upper bound on this thing? And for one thing, this constraint on Q is hard to work with. Q is sort of, given by this. How do you control the sum of the absolute values of the coefficients of Q? Okay. So more massaging, so you say, well, this norm, so here's one thing. If you take any polynomial R, then one thing except that equal sign should be a greater than or equal to sign, the R1. Okay, so what is that thing on the right? Let's take the function R of x and view it as a polynomial in the complex plane. Look at it on the unit disk and ask, what is the maximum absolute value that R takes on? Well, it's really easy to see that on the unit disk, the maximum value that R takes on is never more than the sum of the absolute values of the coefficients. Okay, so we can say, okay, now this norm appears twice, and the inequality goes a particular way, but it goes the right way in both cases for us to substitute, so to replace this thing. And now the other nice thing is that the condition on Q, when you express it in terms of the unit disk about Q, well, Q is just this affine translation of P. So that's just saying that P is bounded above on some other disk. Okay? So the constraint then becomes, okay, so then we get the next version of the problem. Now Q disappears. P of x is bounded by 1 on the disk. So that's a disk of radius mu centered at the point on the x-axis 1 minus mu. Okay, so we've got a picture of it. Let's see, is it there? Is there more? Okay, that's right. So there's the disk d mu. What we know is that P of x is bounded above by something there. We're trying to... Now, how could it be that this maximum is large? Well, P of 0 has to be big compared to the largest value that this thing. It has to be much bigger. Well, there's the epsilon times, but we want P of 0, to be big on the unit disk, and still we want P of x. And now the question is, are there such polynomials? Or what can you say about that? Okay, so next. All right, so take your P and apply a fractional linear transformation. So that kind of distorts the picture somewhat. And now, well, go back one step. Could you go back one step on that? Yeah. So rather than work with this ball, which is off-center, I take a subdisk of it. So I know that P is bounded all on this big disk after transformation. Now I just take a subdisk, which is centered at the origin. That's now next step. Okay, so that's what this little guy is. And then we draw a circle around, which contains the point. So it's sort of P0 we're trying to bound. And now you have some theorem from complex analysis which tells you, well, if you have a function, and let me just now use this pointer. Okay, so I have a function which is bounded here, and it's also bounded on the boundary. Well, then on this circle in the middle, it can't be too big. Okay, and so that gives you quantitative bounds on how big that can be, and then when you plug that in, you get an upper bound on the maximum of this thing, and that upper bound turns out to be good enough. When you translate it, it upper bounds the value of the linear program. The form of the bound is n over epsilon to a power. That power is a constant depending on mu. And so the punchline then is that we've got a polynomial time algorithm for any fixed mu. And an open question is, well, how good is this estimate of the dependence on mu, right? So, could it just be a function like the exponent is logarithmic, or is it even possible that there's a polynomial where mu does not appear in the exponent? Okay. All right, so let me shift gears to the noisy model. Okay, so now again, we've got this model where, let me just remind you, you've got samples coming. Before you see the sample, some positions are randomly chosen and replaced by random bits. So that's what you end up seeing. And our goal is to approximate the distribution f pointwise from these noisy samples. Okay. Well, in this case, in contrast to the lossy model, if you have no prior assumptions on the distribution f, we don't know how to do anything sub-exponential. Okay? So what one does is you impose some assumption on f. And so here's a fairly strong assumption, which is the known support assumption. So what we have is we have some subset of Boolean strings, and we tell you, okay, this distribution f is supported on this set of strings. Your job is just to figure out what the relative frequencies of. Now, when you see observations, your observations will not lie in x. They'll be all over the place because you're going to see noisy things. Okay, so our goal is still to estimate f, and now x, the size of x becomes a parameter. And okay, keep going. Okay, so this is the known. Okay, so Avi and Amir had a paper where they got a dependence which is polynomial, except that the dependence on the set, the known support set, it was not polynomial. It was quasi-polynomial x to the log x. And then Levitt and Zhang improved that dependence to x to the log x. And then in India, and Sijin and I, just recently, this will actually be in Fox next week, got rid of the log x, so it is polynomial. Okay. And I'll also mention that in a separate work, very recent, Shachar, I don't know Zhang's first name, but Levitt and Zhang said we're able to get a result even if, so all these results required you to know mu. Now, let me point something out. In the erasure case, in the lossy case, you didn't have to know mu in advance because you just take some samples and you count how many question marks there are and you'll figure out what mu is. But in this case, where it's noisy, you don't know which positions were corrupted. You have no idea how many positions were corrupted. So if you don't know mu, it's a very different story. Okay, but nevertheless, they're able to do something. And then the other thing to point out is, well, we made this strong assumption that you know the support, or you have a set that contains the support. And I'll mention that that they also have sort of a generic way of weakening the known support assumption, and I'll mention that later if there's time. Okay. Run. Till when am I going?
It's after 20 minutes.
Okay. All right. So I want to focus now on this result of doing the noisy model in polynomial time. So we're estimating f of 0 given samples from, so G is the noisy version of f. Keep going. And, well, so here is a general approach. In fact, I mean, it's a general approach to any statistical estimation problem. It's kind of, so let's imagine that we just take one sample. Okay? Now I'm trying to estimate some parameter. I take one sample. So I want to take a function of that single sample and get an unbiased estimator for the parameter I want to estimate. So I just want that this particular function, the expectation, should be right. Okay. Now, once I have such an estimator using a single observation, I can just take a bunch of observations and take their average, and that gives me something, provided that now what's going to matter is what's the variance of your estimator. So the number of samples that you need is going to be polynomial on the variance of your estimator. And so we want to find such an estimator which having small variance. Okay. So again, we have the support. We know that the support of f is contained in this set X. And our observations are points in 0, 1 to the n selected from the distribution G. Now, G is a distribution which, given f, you can calculate. And the values that G assigns to strings is given by some linear transformation, which is called T mu. And T mu turns out to be this well-known and easy to describe linear operator. It's a Bonami-Beckner noise operator. And again, I'm not going to write down, in the spirit of not putting down technical details, I won't write down what the explicit T mu is, but it's an exercise. You can sit down. You know what it does. What is the probability that, how is the probability transformed? Okay, keep going. Okay, so T mu is the noise operator. It maps the distribution f on 0, 1 to the n to G. So we need a few facts about the noise operator. Okay, first of all, well, think of this operator as a matrix acting on a 2 to the n by 2 to the n space, which is all binary, indexed by binary strings. And it has an orthogonal eigenbasis, and very nicely, that eigenbasis turns out to be a very familiar set of functions, namely the Fourier characters. So for each subset of 1 through n, the Fourier character is the function which maps x to either plus or minus 1, depending on the parity of the number of 1s in x. And the associated eigenvalue for that is just mu to the s. Okay. And then we have the familiar Fourier expansion, which is just taking f and rewriting it in terms of this basis. And the Fourier coefficient, which is the coefficient of f in that basis, well, that turns out to be, you can interpret it probabilistically. It's the average. If you were to select z from f, and you take z and you look at chi-s of z, which is either plus or minus 1, depending on the parity. Okay, so the f hat of s has an interpretation as an average. And then because of the fact that T mu because of the fact that T mu has eigenvectors equal to these Fourier characters, and those are the eigenvalues, you can also write f hat of s as in terms of, you can write f hat of s as the same expectation, but then multiplied by 1 over mu to the s. Okay. All right, so next. Okay. So now again, what's our goal? Our goal is we want to take a single observation and use it to estimate f of 0. We want to come up with an unbiased estimator. Now, we said that g hat of s, well, that's the expectation of chi-s of z, where z is sampled according to g. Now, remember, we are observing samples from g. So if we take one sample of g, then we plug that sample into chi-s, which we can do. We just look at how many, whether the number of 1s in z is even or odd. And that will be an unbiased estimator for the Fourier coefficient g hat. Now, we don't want the Fourier coefficient g hat. We want the Fourier coefficient f hat. So, well, we just multiply it by 1 over mu to the s. So now we have an unbiased estimator of f hat. And then we have the following, standard thing, which is f at 0, which is what we really want, is just the sum of all the Fourier coefficients. So if I add up all of, back up. If I add up all of those estimates, I get an unbiased estimator. Okay, next. So we have a nice unbiased estimator of f of 0. Are we done? Well, no. There's two problems. I mean, we have an unbiased estimator, but one thing is, this unbiased estimator is a sum of 2 to the n terms. So we don't want to add up things, take 2 to the n times. So it takes a long time to even evaluate this estimator. And now the other problem is that the coefficients are exponentially large. And so that's the bigger problem, which means that the variance of this estimator is large. Okay. So, this doesn't work just because we have an estimator, but it's unbiased, but it's just the variance is too high. Okay, next. Okay, so again, our goal is to find a function from 0, 1 to the n to the reals. And we want this to be a good estimator. Okay. So let's formulate. Well, suppose we have a function c defined on 0, 1 to the n, and f of 0 happens to be the inner product of c and f. By inner product, I just mean pointwise inner product, the sum of c of x times f of x over everything. So that's the inner product. So, you use the standard Parseval, which says that we can re-express that as an inner product of the Fourier coefficients of the two things with an appropriate normalization. And then replacing f hat by g hat, you get another sum. Okay, and so now here's what we get. So now we have something, I want to emphasize this thing. The form of this is that f of 0 equals this. But it's a sum of something times g hat. But we already know a way of getting an estimator for each g hat. So g hat is estimated by taking a single sample and plugging it into chi-s. So if you form this summation, you get an unbiased estimator of f of 0. And the point about this is this works for any choice of c for which f of 0 is equal to cf. Next. Okay. All right, so we have that for any c satisfying that condition there, this thing offers us an unbiased estimator. Now, if you want to satisfy that condition up top, there's a really natural choice for c. You want to get f of 0, so put weight 1 on c of 0 and put weight 0 on everything else. And that will give you the inner product. And if you do that, you just recover exactly the same estimator that we talked about before that had variance too high. Okay, so the question is there a better c? So, well, isn't that c there, isn't that the only c that works? Because you need it to work for all f. Well, it is true, it's the only c that works for all f, but now here's where the assumption that we made comes to the rescue, so that's next. The known support, we only need that condition to hold provided that the support of f is a subset of x. And that means that what we would like is c of 0 should be 1, and c of x should be 0 for all x and x, but we are completely free to choose c for x outside of x. Okay, next. Okay, so now we want to pick c satisfying all these conditions so that the estimator has low variance and it's easy to compute. Keep going. And so now, although the previous papers didn't quite formulate things in this language, but essentially you can reinterpret what was done in the previous papers as just getting increasingly better choices for the function c. Okay. Next. Okay. So all right. So we want to satisfy those conditions up there. We want it to be low variance and easy to compute. And it turns out that what you would like is the demands to have low variance and easy to compute. So the initial conditions are on the values of C. And now the conditions that give you low variance and easy to compute are conditions on the Fourier coefficients. So first of all, you want the Fourier coefficients to be non-zero only on small sets and on not too many sets. And also, you don't want the Fourier, any individual Fourier coefficient to be too big. So now it's kind of a mathematical engineering problem. Just find a C which satisfies all these conditions. And so Avi and Amir constructed such a thing, except C, that W should be a C, via this scheme called partial identification. And the only catch was that what we'd really like is that it should be non-zero only on, well, on not too many sets. They get an upper bound of order log x, but that leads to the following bound, which is that the complexity of the estimator, that the size of the support of the Fourier thing could be as large as like n to the log x. And so that they get only that bound. Okay, and now Levitt and Zhang, so their method is they break it up into two parts. They say, well, let's take our set x and let's define w of x to be the maximum Hamming weight of any string. Hamming weight is just the number of ones in the string. So x is the support, and their thing is going to work nicely if this known support only has low weight strings. Okay? And what they do is they build it, and the complexity now is n to a power where that power is logarithmic in this maximum weight. Now, if the maximum weight is n, which it could be, this is just like no better than what Avi and Amir did, but if w of x is small, okay, and now what they did is they have this very clever reduction which takes the general case and reduces it to the case that w of x is small. And so that gives them this n to the log x complexity. Okay, next. All right, so now let me say a little bit about what we do. So, so we want to build C. So now what we do is we also use the same kind of approach as Levitt and Zhang. Our complexity will again depend on the weight of x, the maximum weight. But instead of being of the form n to the log weight of x, it's of the form, the dependence on w of x is exponential in w of x. That's worse, because theirs was exponential on log of w of x. But the base of the exponent is only 2 rather than n. Okay. And so that means if w of x happens to be less than log x or is order log x, then everything's polynomial. So then we could hope to, next. So we can hope to use the same reduction that Levitt and Zhang used, but unfortunately that reduction is not all purpose. It depends something on the characteristics of the function c, so it fails in our case. And so the goal is to sort of, now we found a really nice c that works there, so now we go back and redesign c, but now keeping the reduction in mind so that the c that we get, you can apply the reduction. Okay, next. Okay, so so here's the, so before we do that, before I show you about redesigning, here's the first C. So this is a picture of the, it's a picture of the cube, Boolean cube. The zero, it's oriented so that the all zeros point at the bottom and the all ones pointed to the top, and think of it as a partially ordered set going upward. You take x, which is the support, and d of x is everything in the support and everything that lies below it. Anything in the support. Okay, next. Okay, and now for any particular point z, we're going to define uz as just the function on the cube which maps something to 1 if it's above z in this picture and 0 otherwise. Okay. And now our function c that we propose, Well, you know, we can't go into the details of that function, but I want you to see that it's a fairly simple function. It's a sum of these nice simple functions u's with coefficients plus minus 1. And it should remind you at least a form of some sort of inclusion-exclusion kind of thing. And that is part of what's going on, and that's part of what makes things work. So, you know, this particular form will guarantee that C will be 1 at the origin, and it will be 0 on all of d of x. And when you do this and you work out what it gives you this complexity that I mentioned before. Okay? So, as I've said, but it's incompatible with the LZ reduction, so we can't get rid of the assumption that W of x is small. Okay, next. Okay, so we're going to try to redesign C. And so the key properties are that C of 0 is 1, C of x is 0 for everything in d of x. The support of the Fourier of the spectrum is also limited to d of x. So that's sort of the, you know, slightly non-trivial property that we get out of there. And then the other is the other property. There was another good property, which is also that the values of the Fourier spectrum are small, or not too big. But the bad property for the L's, so when we use C just on x, we don't really care what the value of C is in this part, in this region. The value, because those values will get dot product with values of f, which are all 0 in there. Okay? But when you use the LZ reduction, what happens is you do have to pay attention to the values of C in the upper region. So the problem is our values of C can be exponentially large 2 to that. Okay, next. Okay, so these are the nice properties, and now what we're going to do is construct a function similar to C, but with 4 improved. So instead of the values of C being exponential with base 2, we can make the base as small as we want, 1 plus delta to the n. But then 2 is relaxed a bit. 2 was the condition that inside d of x, C was always 0. Now C won't be 0, but it'll be small. Small depending on delta. Okay? And now, when you do everything, now the LZ reduction does work on this function. And then when you combine that with the properties of this thing, then you get the whole polynomial time estimator. Okay, next. Okay, you know what? We're running out of time. So skip this slide. So final remarks. Okay, that previous slide was just like a hint of how we actually do the reconstruction, but you know, it's okay. All right, so some final remarks about this thing. Next. Yeah, so I mentioned that there's this KSA assumption. So the results for the noisy case rely on the fact that you have this set X. The question is, can you weaken the assumption? So there are 2 natural ways to try to weaken the assumption. One is the bounded support assumption. So that says that the support of F is at most K. That's just the size of the support. You don't know what the support is. You just know that it's supported on. And then you would like the thing to be polynomial in K. The other assumption is lower bound assumption, which just says that that wherever f is non-zero, wherever the distribution is non-zero, the value of the probability is not too small. Okay? So the first assumption implies the second one does not imply the first. Okay, but they both, you know, seem to be, well, the first one is really weaker than the known support. The second one is not weaker, it's incomparable, but it's psychologically weaker than the known support assumption. You still don't know anything about where the support is. And so there was a reduction, a general purpose reduction, which showed that if you had a solution under KSA, then you get a solution under the bounded support assumption. There was a little problem, though, which is that if you analyze, the proof is not quite right, as I think Avi and Amir realized, and we rediscovered last week, and that result. So, but the reduction works just as well does work under the lower bound assumption. Okay. What that means, though, is that the literature, including our paper, is sort of populated with claims that we solve the problem under the bounded support assumption. Those claims are not true. Although Avi and Amir's paper has that claim, and it is true for their because they have a sort of a special purpose reduction instead of this general reduction. But it is true that we get solution under the lower bound assumption. Okay, next. Okay, so wrapping up. So open questions. One is, can you weaken the lower bound assumption? Is the bounded support assumption, or maybe no assumption at all? Can this thing be done? What's the right dependence on mu? So I didn't mention it, but at the end, our algorithm is going to be polynomial for fixed mu, but the exponent is like 1 over mu to the 4th. Again, does the dependence have to be of the exponent have to be on mu? Could it be just logarithmic in 1 over mu, et cetera? And then the unknown mu case, Levitt and Zhang have some progress on that, but it would be nice to get something polynomial. Okay. Thank you. Oh, last. One more slide, please.